Finally, we use all the machinery that we have built for MDPs to solve the real problem that we are interested in, that's reinforcement learning problem. Reinforcement learning is essentially the problem of solving an MDP, finding an optimal policy for an MDP when the transition model and the reward distribution may be unknown to the agent. So how can we imagine to do anything in this case? Well, because even though we don't know the underlying transition model and reward distribution, we do get to observe samples from it. And the idea is to use these samples to learn the model while looking for the optimal policy. Here is the precise formulation of the problem. The agent starts at some initial state S1. Then in every round T, the agent observes the current state, takes some action AT from the action space, and then observes a reward RT and the next state ST plus 1. As before, the reward distribution is fixed by the state and the action, and its expected value is given by some fixed number RSA for every state and action. Similarly, the transition probability vector is also fixed for every state and action. However, the main difference from the MDP model is that now the underlying distribution of reward and the transition probability matrix is not known to the agent. The goal is same as before. We want to find an optimal policy, that is a policy that maximizes the expected sum of discounted rewards. Now, even with the model parameters R and P unknown, you can imagine that we should be able to do the same things as we did earlier with value iteration methods or policy iteration methods, if we were able to generate a lot of samples for every state and action so that we can learn the model accurately enough. The idea here is to look at methods which can do this efficiently. We will look at a method called Q-learning, which works on very similar principles to value iteration and policy iteration methods, but unlike those methods, it doesn't need to know the model parameters like transition model or reward distribution to make its decisions. Q-learning uses Q values instead of value function to choose actions. The Q value informally for every state and action is defined as the value of taking action A in state S, assuming that from the next state onwards you'll do the right thing, take the best possible action. Formally, the Q value for state S and action A is defined as the sum of expected reward for that state and action plus the discount factor times the expected Q value, the best expected Q value in the next state. From Bellman optimality equation, you can observe that the Q value for optimal policy pi will satisfy this recursive relation, that is, it will be a fixed point of this equation here, and the Q value for the optimal policy in every state will be equal to the optimal value function. The idea in Q-learning would be to use the observations obtained during the process in order to find a fixed point solution to this recursive equation. Here is how it works. The Q-learning method proceeds in discrete rounds and maintains an estimate of Q values for every state and action. Then in every round T, after observing the current state ST, it chooses an action AT greedily by maximizing the current estimate of the Q value. Then it takes that action, observes the reward, and observes the transition to the next state. Using these observations, it updates the Q estimates, but only for the current state and current action. It uses this formula to update the Q estimates, and to understand this formula, let's look at the real definition of Q values. So what it's doing is, it is using the observed reward as an estimate for the expected reward in this state and action. It's using the observed next state as an estimate for the expected next state in this expression, and uses this estimated expression to update the Q values. An important thing to observe here, as I pointed out, is that the Q values are updated only for the played action in the current state. The Q values estimated in this way would converge to the true Q values if every state is visited infinitely often and every action is played infinitely often. However, unfortunately, the greedy method of choosing action in this way can mean that some states and actions may not be explored enough even if you run this algorithm for infinite rounds. Here is a simple example to illustrate this problem. Here we have a simple MDP with two states, S1 and S2, and two actions. What happens on taking the first action is shown by black arrows here, and what happens on taking the second action is shown by the red arrows here. Let's say we start the problem starts in state S1. Now here, if we knew the transition model and the reward distribution, then we know that on taking the first action, the black arrows, the immediate reward may be -1 with 0.6 probability, but with 0.4 probability, it will be +1. But more importantly, it will take us to a better state S2 where the reward is very high. On the other hand, the second action, the red arrow, will always give +1 reward, but will never take us to the very good state of S2. So clearly, if we start in S1, then taking the black action is the better policy here. Now let's see what Q-learning does in this case. Now let's see what Q-learning algorithm would do here. The algorithm starts in state S1, but it doesn't know the transition model or the reward distribution. It only gets to observe the reward and state transitions. It initializes Q values with some arbitrary initialization, let's say 0. So there are 3 possible combinations of state and action here, and let's initialize all of those Q values to 0. Now let's say the algorithm decides to play the good action, the black action, in state S1 to start with. But when it plays this action, it sees the transition back to state S1. Now this can happen with 0.6 probability, so it is quite likely that this might happen. Now looking at this transition, the algorithm updates the Q value of S1A1 to -1. Now in the next iteration, it looks at the current Q values, and it's still in state S1, so it sees that this Q value is better and decides to take action A2. And it observes the reward of +1 and transition back to state 1. So it updates the Q value to 1. Now in the next iteration, it again compares the action A1 and A2 in this state, and again decides that A2 is a better action. It will update the Q value to 1 plus gamma now. The rounds will proceed in this way. The Q value of S1, A2 will keep getting updated by addition of gamma squared, gamma cubed, and so on, until it will converge to 1 over 1 minus gamma. On the other hand, because we only update the Q values for the state visited and the action taken, the Q values for this state and action and this state and action never change. So even though we run this algorithm for infinite rounds, we will keep playing action A2 in state 1 and will never converge to the true Q values for these other states. This example may seem extreme, but this situation can actually easily occur, even in more reasonable looking examples. The underlying problem is this. Before enough samples are obtained, the less explored states in action might look bad due to empirical errors. Then the greedy way of choosing the actions will ignore these state and actions and pick the suboptimal actions. And since estimates are updated only when a state is visited or an action is played, the estimate for these less explored state and action will never improve. To avoid this problem, we need exploration. A simple strategy for including some exploration for the underexplored state and actions is to use an epsilon greedy strategy. The idea is simply to take the greedy action suggested by Q-learning with 1 minus epsilon probability, and with small probability epsilon, just play a random action. This simple strategy actually works surprisingly well in practice, even though more sophisticated strategies have been proposed for larger and more complex problems in literature. Here is an interesting trivia. A version of Q-learning with epsilon greedy exploration was recently used by Google DeepMind to design reinforcement learning agents to play Atari games using only as observations the game screen pixels and the game score. Using these observations, the Q-learning based algorithms could in fact achieve human-level performance for 49 Atari games. If you're interested to see this in action, you can search for Google DeepMind Atari games on YouTube.